So today we are going to study this Kleins construction. So let me write this Kleins construction. Kleins construction method facilitates to draw both velocity and acceleration diagram on the same configuration diagram itself. The configuration of a slider crank mechanism is shown in the figure along with its velocity and acceleration diagram. Now, if you draw a slider crank mechanism, let's say this is our crank connecting rod. Crank is hinged on one end. Let's say this is OA is our crank, and the other end of the connecting rod is connected with a slider. Let's say the point on the slider is B and the fixed point is G. So this is a slider crank mechanism, and we have already discussed about how to draw its velocity and acceleration diagram. So let me repeat. For the velocity diagram, you choose any point and the space diagram. Okay, let it be O and G, because we have capital O and capital G, the same link which are fixed here in the mechanism. And one more thing I would like to add here, the relative velocity of point A with respect to O can be represented by this line, which is normal to the crank. Okay. Now, if you are interested to draw the velocity diagram, the first step will be to measure this VAO. Okay, so this VAO will be basically the angular velocity VAO multiply with the crank length, that is OA. So we'll get the magnitude, and direction we know it is normal to the crank. Okay, so here you first take a point OG. There, from there you draw a line which is parallel to this BO over here. So this is BAO line, and you'll get this point A over here. Okay, because we know the magnitude, so with some suitable scale you can draw this OA line, OA vector. Okay. The next step is to indicate the velocity of this point B with respect to the fixed guide. Okay, which is of course in horizontal direction. Okay, because the slider always moves inside the guide in horizontal axis. So we'll draw a horizontal line indicating the direction of point B with respect to G, whose magnitude is unknown to us. So now what we'll do, we'll draw a line perpendicular to this connecting rod. Okay, so we'll draw a line perpendicular to the connecting rod, and both these line will intersect at point B. So this will give us the velocity of point B with respect to A. Okay, and upon measuring we can find out this BG and BA. So this is our velocity diagram. Velocity diagram. The next step is to draw the acceleration diagram. Here what we'll do, again you'll take a fixed point here O dash G dash in the space diagram, and you will represent a vector which is the radial component of acceleration of point A with respect to O. Okay, because it is only having constant angular velocity omega, no alpha is given to you, so we'll have only radial component which is parallel to the crank OA. So let us draw a line parallel to the crank. So this will be our A subscript AO, and we'll find our A dash point. Okay. From there we'll draw the acceleration of this connecting rod, and here this acceleration will have two components. One will be the tangential component, another will be the radial component. Okay, so to represent that, first let us draw the radial component, which will be parallel to the connecting rod AB. So now you draw a dotted line A dash X, okay, which is parallel to the connecting rod, and it represents radial component of acceleration of point B with respect to A. And AR BA, we know it is B square BA divided by AB. BA you can obtain from the velocity diagram. Okay. Now after getting point X, the next step is to draw the tangential component, and we know its direction will be perpendicular to the connecting rod. So you draw a line perpendicular to the connecting rod, a dotted line basically, okay, and its magnitude is still unknown. Okay. So let us write here A tangential BA. Next step will be draw a horizontal line which will indicate the acceleration of this point B with respect to point G, because it will be of course in horizontal direction. So draw a horizontal line here. So this will be your acceleration of B with respect to G. Now both these lines will intersect at B dash. We join B dash A dash, and this will give you the total acceleration of B with respect to A, having two components. One is tangential component perpendicular to the connecting rod AB, and the radial component is parallel to the connecting rod ARBA. So this is our acceleration diagram. Acceleration diagram. We have already done this. Okay, for the slider crank mechanism, we have already done this. Now, in this method of Klein's construction, we'll represent both this velocity and acceleration diagram on a same space diagram. How to do that? Okay. So, in order to have that, let us draw this mechanism once again, right? So, this is our slider, as I've already told you. This is the connecting rod. So, this is O, this is A, this one is B. Okay. Now, remember the first step you can write for the velocity diagram. First step is to extend this line BA and to draw a line perpendicular to this OB. Okay, so we'll draw it. So both these lines will intersect here at small b. Okay, now let's say this is our small o, this is our small a, and this point is b. So this triangle O, A, and B will give us the velocity diagram, okay, of the slider crank mechanism, which is rotated through 90° in anti-clockwise in compared to the original velocity diagram. Okay. Now, next step is to get the acceleration diagram. For this, the first step is to draw a circle with small ab as the radius. Okay, so you draw a circle with small ab as our radius. Okay, let us erase it. And next step is to draw a circle with capital AB as the diameter. Okay, so with capital AB as the diameter, draw another circle. Let us complete that. Okay, this is our circle. Now, next step is, let's say both these circle intersect here and here. You can see, and you join them. Okay, you join these two intersection points. Okay, let's say the point here it is capital C and here it is D. So the line CD, suppose it intersect the capital OB line here at, let's say, E, and the capital AB here at B1. Okay, then we can say that this portion, this hatched portion, is our acceleration diagram. That is, if I write this as O1, this point, same point as A1, this point as B1, and capital E will be our acceleration diagram of the slider crank mechanism rotated through an angle 180 degree as compared to the original acceleration diagram. So here we can see we are obtaining both this velocity diagram and acceleration diagram in the same space diagram. So this is our space diagram. Okay. So this is known as your Klein's construction. Klein's construction actually. Okay. So let me write down the steps that we followed to draw the velocity and acceleration diagram. So for the velocity diagram, what we did that first you produce line BA, capital BA, and draw a line perpendicular to perpendicular to OB through point O. Then second step will be the intersection of two lines locates a point B. Okay, then the triangle small o small a small b is the velocity diagram of slider crank mechanism rotated by 90 degree. Okay, you can say anti-clockwise. Okay. Then next step is to draw the acceleration diagram. So here the first step is draw a circle with small ab as the radius and a as the center. Second, draw another circle with capital AB as the diameter. Okay. Third step will be join the point of intersection that is capital C and capital D of the two circles. Okay, let CD CD meets OB at, you can see here, let CD meets OB at point E and the line AB at B1. Okay, then we can say, then this O1, okay, O1, here you can see O1, A1, B1 and E. Okay, O1, A1, B1, E is the acceleration diagram of the slider crank mechanism rotated by an angle 180 degree. Okay, so this was all about your Klein's construction. It is a very important parameter used in machine dynamics. Okay, usually you'll get short notes on this in your exam. Okay, thank you.